Look at the interface for this digital archive. You can interact with different AI personas to retrieve answers from a lifetime of data. But this polished exterior conceals a difficult reality. The underlying large language models possess zero inherent memory of your data. To make an AI useful over private records, developers have to solve a structural problem. They must build an orchestration layer that physically connects these stateless reasoning engines to thousands of messy, isolated personal files. This requires balancing strictly competing engineering demands. A developer needs high-end reasoning capability for complex queries, but must also account for strict local privacy constraints and the high cost of constant API calls. A structural data pipeline provides the foundation that allows a simple prompt to function across an entire archive. We are going to deconstruct exactly how the system works. Tracing how it ingests chaotic data, how it executes stateless tool loops, and routes queries to minimize costs. Mastering AI application design requires engineering these robust retrieval architectures. Simply writing an API wrapper around a language model is no longer sufficient. The vast majority of the code in this application has nothing to do with artificial intelligence. The bulk of the engineering effort is dedicated strictly to data ingestion. This pipeline must parse completely unstructured, idiosyncratic data exports. It pulls heavily nested JSON from Facebook, raw CSVs from iMessage, and decodes raw RFC 2822 byte streams from IMAP email servers, normalizing them into standardized database rows. This normalization exposes the contact problem. Different platform identity systems fragment a single person's footprint. A person might appear as David on Facebook, an email address on IMAP, and a phone number on WhatsApp. Entity resolution must converge these disparate identity strings into a single unified node. To prevent false positive matches, the ingestion pipeline relies on explicit manual mapping and heuristic merges, strictly enforcing a 0.85 Jacquard similarity threshold before combining contacts. Once the raw data is structured and linked, a secondary ingestion phase begins. The system runs text from emails and metadata tags from photos through local embedding models. The resulting numerical vectors are stored locally in dedicated SQLite vec tables. This creates the mathematical foundation required for semantic similarity searches later on. If an LLM queries a database filled with fragmented identities, it will return an incomplete answer. Its reasoning ceiling is dictated strictly by the cleanliness and unification of this underlying entity graph. Even with a perfect database, LLM API calls are inherently stateless. The model possesses no memory of the archive or any previous conversational turns. To bridge this gap, the architecture requires a defined tool calling layer. This is a suite of strictly scoped functions the AI can invoke to query the backend. The execution loop begins when the LLM detects a gap in its knowledge. Instead of hallucinating an answer, it pauses generation. The model signals its specific data requirement by outputting a structured JSON payload containing the necessary query parameters. The Go backend intercepts this JSON payload. It takes control, managing the execution of the requested tool against the database. The database processes the query and returns the matching records as a plain text result. Finally, the application injects this newly enriched text back into the conversation history and returns it to the LLM, which processes the context without realizing a previous request was made. This retrieval cycle is highly iterative. The model can repeat this loop up to 15 times, doing detective work to systematically build a complete answer. The AI dynamically decides which tools to use. It might deploy deterministic keyword tools for references or semantic vector search tools to bypass vocabulary mismatches and find conceptually related content. By wrapping a stateless reasoning engine in this architectural loop, a static language model becomes an active, investigative agent navigating private data. Sending every user query to heavy, hosted APIs introduces severe latency and drives up token costs. To solve this, the application employs an auto-routing architecture designed to triage incoming requests dynamically before they reach the cloud. A lightweight local AI model, running entirely on the user's hardware, acts as an intercepting classifier. This local model analyzes the user's prompt alongside system metadata and outputs a JSON payload. This payload classifies the request's exact level of complexity. If the payload indicates a simple factual lookup requiring one tool call, the system routes the request to local execution. If the payload flags a multi-step reasoning task or complex persona generation, it forwards the query upward to a hosted cloud model. This classifier also performs context optimization. If the JSON payload determines that large reference documents or extensive psychological profiles are unnecessary for the question, the system actively strips them from the prompt before routing. If the selected hosted provider fails due to rate limits or an outage mid-session, a pre-configured fallback chain automatically routes the request to the next available API. This intelligent routing framework drastically reduces API token costs and lowers latency, while explicitly preserving peak reasoning capabilities for the tasks that truly require them. Scaling this architecture introduces hardware constraints. A personal archive can contain tens of thousands of images. Running a classification backlog sequentially through a local model takes multiple days. To handle heavy data operations, the system transitions from slow sequential processing to massive, high-speed, serverless parallel execution. The architecture implements on-demand GPU worker pools. When triggered, dozens of concurrent Go routines spin up, all pulling from a single shared work queue. This setup uses a dual-worker fault-tolerant strategy. A persistent local worker handles the baseline load, while serverless run-pod workers spin up simultaneously to handle large immediate bursts. Serverless nodes incur zero idle costs. The user is only charged when requests arrive, turning a multi-day local task into a highly efficient one-time burst charge. Offloading bulk asynchronous tasks to parallel cloud workers successfully protects the baseline responsiveness, ensuring the user interface never freezes while the database updates. Looking at the complete system, we see data ingesters feeding vectorized databases, managed by a continuous stateless tool loop and an intelligent routing classifier. This orchestration engine seamlessly balances local data privacy with high-end cloud capability and serverless compute scale. Building this level of complexity, including the 8,000 lines of code required for the ingestion pipeline, required a fundamental shift in the development process. To handle the project scale, the workflow moved toward agentic direction, utilizing tools like Claude Code and Cursor to design and refactor entire features end-to-end. The engineering process focused on specifying macro-architectural constraints, like API tiering and security protocols, while AI agents implemented the granular repository patterns and idiomatic Go boilerplate across dozens of files. The data pipeline and orchestration layer represent the core engineering achievement, providing the environment that allows modular language models to operate at scale.